So now the iterative formula, which is given by here, can be used to find an approximation for alpha from the previous question, yeah? So C, by taking x1 equals 0.7, find the next two values, and remember to give it to 4dp. Now here's a cool trick here when you calculate, and you probably already know this because you're probably you're A-level math students. So what I would do is firstly put the value they want, put 0.7 in the calculator and press equal sign. Now your calculator is going to record this as an answer of 0.7. So what I want you to do now is to copy this expression as I did here and just write 3 over 2 times answer plus 4 sign bracket answer. This usually works, this works with Casio calculators, and I'm sure it works with like Texas and other brands. Anyway, what I want you to do here now is just press equal once and don't delete nothing. If you press it once, you get this value. If you press it again, equal sign, you can get this value. The reason why is because the previous answer is now the new answer. So if you're going to press equal again after this, you're going to get x4 and then x5. So yeah, you don't have to keep repeating it. You can just leave the answer button and just keep doing it. So yeah, definitely learn that trick. It's really, really helpful in exams. Now, that's done. So part D. By choosing a suitable interval, show that alpha equals this term, alpha equals 0.7283 to 4 dp. Okay, so what this means is that because we know it's been rounded to 4 decimal places, there must have been an upper and lower bound. So if you think of error intervals, it's always the same answer plus minus like an extra 5 at the end. So that's what I did over here. Test using alpha equals a term plus minus 0.00005. Because if you were to round these values, you'll get this answer here to 4 dp. I mean, this has to be just less than 5, but yeah. Now, all you got to do is really just call this the first alpha and second alpha. You just plug into the function equation, which, by the way, this function is from the previous question, yeah? We want to test if this value can give an answer above and below 0. That's the whole point of these questions, to see if this equation can give you an answer above or below 0 with our given values here. So for example, I plug in the first alpha value, this one, the 0.72825 into the equation here, and I get a negative answer like just below 0. I plug in the second one, I get an answer just above 0. So yeah, we can, and because of this, you give a conclusion. You could just say something simple like, hey, there's a change of sign. So what that means is that it crosses 0. So yeah, the answer must clearly be somewhere around here because it's so close to 0. So the answer is between these two. And that's it. That's all they want you to do. Nothing fancy. Very simple question. Just bounce. Okay. All right. So let's move on to the next bit. All right. Number 12. Oof. Differentiation. My enemy. So let's have a look. So again, I put so much detail on this page. So we're going to go and discuss this step by step, how I came to this conclusion, and we're going to quickly summarize this using some fast techniques. So figure 4 shows a right cylindrical water tank, so in the form of a cylinder. That's why I got the volume of cylinder over here just in case. The diameter of the circular cross section of the tank is 4 meters, so that's diameter, meaning the radius is half too. And it also has a vertical height of 2.25, the whole tank, whereas the water so far up to H after a certain time is H. Now water is flowing into the tank at a constant rate of 0.4 pi meters cubed per minute. Stop right there now. When they say this, it means that they want to find this is a derivative equation. This is a change of rate, and a change of rate is always in the differential form. So I put over here water flowing into a tank. This is literally the change in the volume meter cube over time. So dV, I call it 2 because there's 2 types. There's two things going on. dV over dt, which equals positive 0.4 pi. It's positive because it's entering the tank. There is a tap at point T, which is over here at the base of the tank. When the tap is open, water leaves the tank at a rate. So again, another derivative at this rate in meter cube per minute. So again, it's another dV over dt. So it's the first one I wrote here. Water leaves the tank. So this is, I call it dV1 over dt. And because it's negative here, it's because it's leaving the tank, hence the negative sign. So yeah, that's done. Where H is a height. Now, show that time t minutes after the tap has been opened that the height of the water in the tank satisfies the differential equation. We need to prove this equation. We need to formulate it. Now, a quick tip. We need to firstly count what variables we have. For these kind of questions, always check your variables. We know we have a volume V. Because we're dealing with meter cubed, so it's a volume, and we have a nice equation there. We also have h, which is the height. We also have time, because we always have time change rate, so that's always a given. So this means we can formulate an equation with all three differentials, with all three variables. Now, since we know one of them is dh over dt, I would write that down. And now I would write another term, which I don't know, you can make in any order, but you can write another term which you can kind of imagine cancels out of dt. Like just in a theoretical sense, if these were to cancel out, you'll be left with dh over dv. So that's why you can equal it like this. So you can make an equation which has dh over dt times dt over dv. These two cancel out to leave dh over dv. Now don't actually cancel out. The whole trick is that you need to substitute the values of this differential and this differential, and then just tidy up to make it look like that. Now, for the volume, now just to take our time here, we have this derivative right here. It's just upside down from the first two versions. This is dv over dt, and same here. Because we have two, we always collect them. So you're going to add these up to make a total dv over dt of 0.4 pi plus or minus 0.2 pi root h. That would be the total dv dt. Because it's upside down, it'll be 1 over that. As for dh over dv, you need to work that out. So to work this out, we need to recognize the volume equation, which is volume equals pi r squared times height. It's pi r squared because you've got area of circle, and it's height because there's some sort of height. So we're only interested in the water level, yeah. And then realizing that the radius was 2, it's going to be 2 squared, so it'll make 4 pi. So 4 pi h. And then differentiating this in respect to h, so it'll be dv over dh. H disappears, you're left with 4 pi, and that's it. Now you plug in 4 pi here. And again, just like this one, this is upside down. So it's going to be, so dh over dv is the reciprocal of this. So it's 1 over 4 pi. So that's it. So we've got 1 over the sum of these two terms and 1 over 4 pi. So it should look a bit like this. Okay, so dh over dt times 1 over the sum of the rate of change equals 1 over 4 pi. Now all I did here is firstly cancel the pi's, because well they're everywhere and you can cancel them out. And then I just times 4 across, and I times these lot across as well. So this term goes on the right hand side and 4 goes there. And then to prove this equation here, just times all of this by 5, because we know if you times 4 by 5 you get 20, and you just have to pray and hope to God that this will give you the same, and it does. And that's it. That's how you get the rate of change, the equation given. Bit tricky, but it's just a case of really try and break down as many steps and show some clear proof. Okay, anyway, let's move on to the next bit. Okay, so that's done. We complete A. So B. So at the instant when the tap is open, T is 0 and H is 0.16. Okay, so I put a little note here. What this means is that when time is 0, we get the initial H1 is 0.16. So that is from the beginning. However, after a certain time has passed, we get a height of 2.25. Well, actually, that's part B's reading. So use the differential equation to show that the time taken to fill the tank to a height of 2.25 is given by this. So yeah, the final time, after a certain time, this will be the final height. Now to solve this, yeah, you just have to solve this derivative. All I do in this one, my tip, is to firstly collect all the h terms together. So I treat this as one term, 2 minus root h. I divide all this to the left, so it becomes like this. And then I times dt to the right, or dt across, so dt moves to the right. And now we have it. I mean, for these kind of questions, you must always get the h terms together or the t terms together. If you don't have t terms, then well, you can just stick a number term. But h terms must go with dh. And I just pop in an integral sign for both, and you're gonna have, there we go, 20 over 2 minus root h dh. And now we just integrate. Well, actually, don't even integrate. You just have to make it show this form. And yeah, you just plug in the values of h1 and h2, which is a given. Done. And oh yeah, integrating dt, well, that's just 1 dt, so it just becomes t and plus c, and you're done. But we're not concerned, we just want this equation. Alright, so yeah, let's keep going. So now, using the substitution h equals 2 minus x all squared or otherwise, find the time taken to fill the tank to a height of 2.25. In other words, evaluate. So let's have a look. So using substitution, I said let h equals 2 minus x all squared. Now differentiating this one is easy, dh over dx. firstly draw the power 2 and then differentiate it inside, and you get a -1. So it'll be -1 times 2 is -2. The power drops to 1, so it looks like that. Now, as always, yeah, for these kind of questions, you always want to find an expression that replaces dh. So make dh a subject for this one, times dx across, and you have something like that. That's perfect. And now you want to replace this h as well. So we already have it here. So for root h, well, you can just put a square root sign here and get rid of the power 2. And that's fine. Now, before we plug everything in, let's go ahead and change our limits. Because remember, these are h limits. We need x limits. So rewriting this one and making x a subject, square rooting it, and then putting x on the left and root h on the right, we should get x equals 2 negative root h. So we can say, okay, so when x is 0.16, h is 0.16, x is 1.6 in a calculator. So you plug it in, and when h is 2.25, you get another value for x. And yeah, let's put that in, and then we just update these values here with the x limits, and then substitute everything back in. So we're going to have 20 over 2 minus root h. Root h becomes 2 negative x, because remember, you just make root h a subject, guys. And yeah, dh becomes literally all of that, -2 times 2 minus x dx. Yeah, so now it looks kind of crazy, but it's really not, because you'll realize something in a sec. So let's look at this. Let's see what we can do to simplify this. With this 20 and -2, if you multiply these together, you get -40, and it's a constant, so you can take it outside integral. That's why it's here. And then if you simplify the bottom, you have 2 minus 2 plus x, so that simplifies to just x, and you're just left with 2 minus x, so just put that on the top line. So it looks like this, and then you got dx. Easy. So that looks a lot more friendly now. Another cool thing is because since you just got a single term x, you can split this up as 2 fractions, and now you don't need to use a partial fraction method. It's just literally 2 over x minus x over x, which is 1. And that's it. Now you just integrate this. And this is a tip. This one is definitely the log, and this one is definitely x. So integrating these two, and you should get 2 ln x, because 1 over x is ln x, and integrating x is 1 is just, well, x. Then you just plug in the values, and we just say when x equals 0.5, you plug in 0.5 here first, minus, then you plug in 1.6, and those two should come to a value like this, minus 1.226, and so on. Then times that to -40, and you should get a time of roughly 49 minutes. Whew, intense. Not bad. Seriously, this paper is challenging. I admit, I spent some time to really try and make the steps easy. So yeah, let me know what you guys think. Anyway, let's move on to the last bit, guys. Oh, how many last bits are did I say? Okay, well, we have up to, let me see. How many questions are? Okay, question 14 I think is the final one. Yep, 14 is the last one. So we got 13 to go and 14. And here we go, guys, number 13. Let's check this out. Only 2 more to go, yeah? So, a colony of ants is being studied. Ooh, I love this one already. The number of ants in a colony is modeled by the equation, where P, I'm guessing, is a population, and is followed by some exponential terms. Okay? So P is the number of ants measured in thousands. T is after the study started. Cool. So you can kind of see that at some point in time, the population of ants is dropped. Seriously, I think ants need their own like civil rights and stuff. This is totally unfair. Now, A, calculate the number of ants in the colony at the start of the study. Oh, very easy. Start of study is over here, so it means when the time is 0. So plug in T is 0 into this equation. And, you know, just doing the maths carefully, you should get 190, so 190,000 ants. Okay? So 190, you'll get 190,000. Now, next one, find dp over dt. So differentiate. So this is straightforward. So differentiating 200 is 0. Now, differentiating this, well, you have a term on top of another term, 2 different functions. So this is the quotient rule. So just like the product rule, we're going to pick our u and v. Our u is going to be the top terms, and v is going to be the bottom half. So when you have that, you differentiate both terms. So let u equal the top half. And if you differentiate this, well, drop the power down. So it'll be 0.6 goes down, becomes 90. So 160 times 0.6 is 96. And you just copy it back. Same for here. Differentiating this time. So 15 vanishes. And then you will e to the 0.8t. So differentiating this, the power term, 0.8 drops. So you have 0.8 times e, and then copy it down. Easy stuff. And thanks to the quotient rule, the way it works is always going to be from v times u prime minus u times v prime, and then all of that over v squared. So this is easy. You just stick the two terms together. So this is quite self-explanatory. I, for some reason, simplified this one. I did 1/6 when you times these two terms, 160 and 0.8 gives you 128. Now e to the 0.6t times the other e term, because they have the same base, you just add the powers, which gave me 1.4t. And all over v squared, which is 15 plus e 0.8, which is all of that squared, literally. And then you can just expand the bracket and then collect like terms. You can get something like this, but I think this is sufficient as it is, minus the v squared bit. This is sufficient. Now, next question. Now, the population of ants initially decreases, all right? So we saw in the graph that initially decreases over here. So this is going to be literally the turning point. You can kind of guess that they probably want you to find the derivative. So using the answer to part P, calculate the value of t to 2 decimal places. Now, we have to set dp dt to 0 because when you're differentiating, you're finding the rate change. So you're finding this is when the gradient is flat. At some point, the gradient is completely straight. So it's 0. So that's why the equation. That's why we use this formula. So when you differentiate this equation, wait, did I even do? Oh no, I already did. My bad. We already differentiated. We just set this equation to 0. Yeah. So when you set this one to 0, this is easy. You can just multiply the bottom half across, and that cancels out immediately. So that vanishes. And then you can plus 32 across, so you have something simplified to this. Now, this is just algebra. So what I did is I just divide 32 and I divide e to 0.6t across, and it looks like this. When you're dividing terms of the same basis but different powers, subtract the powers. So 1.4t minus 0.6t is 0.8t. This in the calculus 45. And now you can just take the natural log on both sides. So that e cancels out, becomes 0.8t. And you have natural log of 45 and divide by 0.8, and you got your result. Straightforward. Very straightforward question. Now, here comes the big boss of the question. Oh, number 14. You're going to hate the integration. Actually, integration is quite easy. But you're going to hate the part C step or part B, whatever it was. Anyway, let's check this out. So, guys, let's have a look what we got here. So, figure 6 shows a sketch of the curve C with parametric equations here. Oof. Given that the point P lies on C, which is intersecting between the line and the curve, and has a parameter of theta equals pi over 3, so literally sub that in, find the coordinates of P. Alright, so this is actually easy. So since we know the parameter is this, plug in pi over 3 to x and y, and you get the coordinates actually. Plug it in and you get 1 and 4.5. And that's it, P is done. Next one, the line L is the normal to C at P. So normal is over here, so this means that it's perpendicular. It is a tangent equation, but it's perpendicular to it as well. So it's completely 90 degrees. Show that you can form this equation. Okay, so that's what the line equation is going to be. Now, we need to ask ourselves, to find an equation of line, as always, is y equals mx plus c. Now, first things first, we need to find what is the gradient at P. What is the m value? Remember, this m value is not the same m value as the normal. Once you find the gradient, we need to literally just find the reciprocal, the perpendicular gradient, which is easy to do. So first things first, let's find dy over dx as always. Now, we cannot find dy dx directly because we have thetas all about. So you could use the chain rule and just say, okay, if you got dy dx, I'm going to write dy here and dx here and smack out d thetas on both of them. So this means, firstly, find dy over d theta over here. And then as for d theta over dx, well, find dx over d theta first. Now, this is just a case of chain rule. To differentiate, to do dy over d theta, looking at the y equation, to differentiate this carefully, all you have to do is observe that this is, you got power 2. So I would firstly drop the power down. And think of it as inside the bracket. When you drop the power, you need to differentiate the inside the power, which is sine theta. Differentiating sine theta gives you cos theta. And now, because you draw the power 2, you got 6 times 2, which is 12, and then you leave the sine theta alone. So you have sine theta to the power 1 times cos theta, essentially that, which is simply like that. As for dx over d theta, you drop the power 3 down, so you got 8 times 3 is 24. And now, and you reduce the power to 2, so you have cos squared. Perfect. And now to differentiate cos theta, you get negative sine theta, so you write negative sine theta. So that's the steps. So quick recap, this is just a fast chain rule. Drop the power down, so it's going to be, for example, y would be 6 times 2 is 12, and keep the sine theta, so sine theta power 1. And then all you have to do is differentiate sine and get cos. Done. Okay. Wow. Anyway, let's move on. If you already know this, we can skip ahead. So I made a quick note as well. This is the chain rule steps right here, where you get y equals d6u squared. So we just pick it. We just let u equals sine theta, and we just differentiate both, and then multiply the final two terms. And of course, substitute u back in, you get that. Same thing applies here. Anyway, let's get to the next bit. We want to try and get this question solved. So once you obtain all of these, let's go back to dy dx. So it's going to be the first term here. Because this is upside, this is reciprocated, you need to do 1 over itself to get d theta of dx, times against dy d theta, like we did over here. So it'll be this over this term, and you should get something like this. Exactly. Now all you do here is literally just cancel down as you go. So you got sine theta up and down, cancel them out. You got cos theta here and cos theta, so cancel one of them, or cancel both, and then you're left with one cos theta term. And then 12 and 24 becomes 2, 1 over 2. So literally it reduces to something simple. And now just remember where we are. This was the gradient we found at point P, but we want to find the perpendicular gradient. So it'll be this answer, you do the reciprocal and then change it to positive, and here we are, finally done. Now let's solve. Now let's plug everything back in. So using y equals mx plus c like I did, we're going to plug this back in, plug in theta pi over 3 because we need that, and plug in the points P to find the value of c. So doing all your things, putting the values in, you'll realize that when you put pi over 3 anyway over here, you should get a gradient of 1. So m is definitely 1. And then this is all 1, so 4.5 equals 1 plus c. Subtract 1, you get 3.5. Hence, we get the equation they asked for. Yeah, that's really it. That's literally it. Now, the final bits. Let's do this. I want to see if there's anything else. C and D. Okay. Right. So let's have a look. So the finite region S shown in figure 6 is bounded by the curve C. Okay, so we've seen this before. Show that the area S is given by two different terms. One which is an area of 4, and the second which is an area of 144 times the integral. Okay. Now, what I recommend for this question is that we should try and break into pieces. If I zoom in over here, let me see if I can. Okay, that's probably a bad idea. When I zoom in like this, you can kind of see that I split this into two shapes. At the point P, I always recommend this, but when you have an intersecting point, always draw a straight line down and realize that you can make some kind of triangle, rectangle, or in this case, trapezium. Now, to recognize this instantly, we can see that, just put this back here. Oops, we can see simply that the point P, as we found earlier, was 1 and 4.5, all the way back here. So let's label this height of 4.5 and x1. Now, to find this length here, this point here, we can see that this is when the line hits the y-axis. When it hits the y-axis, x is 0. So using the line equation, when x is 0, y is 3.5. So that's cool. So now we have pretty much an area bit. So this bit is covered. So technically the first area here is just simply the trapezium rule. We can use the trapezium rule, which is just the height of 3.5, the average of the two parallel lengths times the vertical height. So 3.5 plus 4.5, the average of that divided by 2 times the difference of 1. And that gives you the area of this trapezium. If it's a bit tricky, just use the area of a triangle method. So remember, 3.5 plus 4.5 over 2, and then times the different length 1. Okay. Now here comes the main part. So now we need to find the area under the curve from P all the way up to this point I call W. Now to find what W is, now we need to go back to our parametric equations. So I pop them over here. These are the parametric equations from the early parts of the question, which was here. Okay, and we just have to see that when this curve hits the x-axis, and then y is 0. So I would use this equation here, y equals 6 sine squared theta, and find what theta is. So I can plug into the next equation and find x. So when y is 0, add W, put over here, and Y 0, solving this one, theta 0. And with theta 0, plug into the x1, cos theta is 1 by the way, so x simplifies to 8. So this means this coordinate here is 8. So we're going to be integrating from 1 to 8. And of course, the usual equation is y dx. The y equation dx. Now, what do we do next? So what we do now is we want to substitute a term for y and a term for dx. So it's all written in cos in theta form, and then update the limits of x into theta limits. So one step at a time, guys. Yeah. So for y, we have it ready. It's 6 sine squared theta, so we can plug in directly. For dx, well, we had it in the earlier question. We found where is it? Dx over d theta, which was over here, minus 24 sine theta cos squared theta. So so all you have to do is make dx the subject. So times d theta across, and we should get the expression right here, the highlight expression. So now we replace dx with all of that term that we just obtained. Okay, so far so good. And oh yeah, as for the limits, we can just have a look carefully. So when x is 1, we can say that theta is pi over 3, because we can use the again x equation here. Plug in 1, divide by 8, and then cube root and cos inverse, you get pi over 3. Plug in x is 8 here, and then solve, you get theta 0. So again, update the limits, yeah? Always do it properly as well. When you're changing 8 here, make sure you put 0 top. It looks weird now, but we're going to fix it up later. Okay? Alright, so back to the question. So to resolve this, now all you have to do is multiply this out. It's just collect like terms, tidy up, and fix up. So we got 6 times minus 24 is minus 144, goes outside. Sine squared theta times sine, it gives you times cos, will give you sine cubed cos squared. So just stick the extra 2 on this. So it becomes sine cubed, and cos squared is still fine. Alright, so that part is good. Now, the problem here is that we want to get this long-winded expression. Okay, so it looks nothing like that. But indeed, it actually is, because all you can really do is simply pick one of the terms and just expand it out. Notice how the sine theta is just sine theta, is like is a power of 1. So this is somehow reduced. So what I did over here, I just pulled out sine cubed to the right here and said, okay, let's write this in terms of sine theta and sine squared, because with sine squared, you can modify it as 1 minus cos squared. And if you do that, you're going to have 2 different terms. That's exactly what they want. So do it like that. And then plug this new term, sine theta 1 minus cos squared, into this equation. So replace sine cubed with this, and then you got cos squared there. Multiply this out. So to make it easier, move cos squared in front. So you got sine theta cos squared theta times the entire bracket, and you should get the final expression here. As for the limits, if you just swap the limits, then you can flip the sign, because this will give you like a negative. This will give you the same answer entirely. If you do a small limit minus a bigger limit, you'll get the same answer but a negative version of it. You get a negative answer. Big minus small, you get positive. So that's why we flip the signs too. And yeah, that's it, guys. That's literally part C done. Now let's move on to the final part of this. Okay, so I call this one S just because that's what they call themselves, the area of S. Now, hence by integration, find the exact area of S. Okay. So for this kind of form, since you've got 2 different parts to integrate, which you can combine by the way, but in this case we won't. I would call the first term R1, second term R2. So we're going to integrate. So let R1 be the integral from 0 to pi over 3 of the first term, d theta, and R2 be the second term. So we're going to do step by step here. And when you do it, you can kind of see that, of course, since we replace the integrals, this will be the final form of the answer, R1 minus R2. It's not the only way, it's just something I prefer. So now integrating the first term, the first integral, it's dead easy. When you look at this head on, you got to ask yourself, pass or substitution. The rule of thumb is to always use substitution first. And when you have sine and cos, the tip is to always use u on the bigger power term. Not all of it, just like parts of it. Because if you differentiate, you're going to get a term, a trig form in the same terms of its opposite. And then you can entirely solve it. So always use it, for example, the basic one, like cos theta. So I said let u equals cos theta. Differentiating this gives us negative sine theta. And now all I want to do is make d theta the subject here. So d theta, just times d theta across and divide minus sine theta. You get something like that. Okay. And likewise, the limits, Again, you have to update the limits into u limits because we're working in u's now. So you can say when x is 0, or when theta is 0, plug in theta is 0 into the u equal cos theta equation, so you get u equals 1. When theta is pi over 3, plug it in, you get half. U is half. That's it. So update the limits. And now just go ahead and update everything you know. So going back to this equation, limits updated, sine theta, there's no sine theta expression. There is, but we'll get to that. For cos squared theta, replace that with u, so it'll be u squared. D theta, replace it with d over minus sine theta. Now, this is done. So now, as you can probably see, the sine thetas here cancel each other out. You can take out a negative sign, so, and that's it. Now you have minus the integral from 1 to half of u squared. And that's just u3 over 3. That's just add power 1, divide by itself. Evaluate this, and voila, 7 over 24. For the second integral, it's the same thing, but now you have a power over 4. So you don't have to do these long steps. So it's the same method, except you have a power over 4 instead. Everything's the same. So this becomes u5 over 5, and that all simplifies to 31 over 160. So now with our given values of R1 and R2, we can finally plug into the original equation here, and done. You should get 18.1. Oh, that's it. Anyway, guys, thank you for watching. That's been, for me, it's been one hell of a ride. It was a long question, and yeah, intense. And today, as of my recording, today is Eid, so we're going to be enjoying that today, and I hope you guys are all having a lovely day. If you enjoyed my videos, please give me a like. I admit this was a bit more challenging to recording other questions because there's a crazy number of steps, and I can imagine it gets tiring to listen to all of them. So I try to make it as engaging and, you know, not too dull as possible. But yeah, let me know what you guys think. Give me some feedback, and yeah, I'll catch you guys next time. Ciao.